Yeah, hello everyone. Welcome to System Verilog course, and this is module 3. The topic being discussed will be interfaces and verification examples. The general method of writing a DUT with port declaration is as follows. For example, if you look at this example which is shown here, we have a DUT by name my underscore module. So this has input clock, another input reset underscore n, that is RST underscore n, and a third input which is a 8-bit bus named data underscore in. Also, it has a 1-bit data output data underscore ready, and a 8-bit bus again data underscore out, which is an 8-bit. So these are all the port declarations which we in traditional way do for a DUT or design under test. The problem with such Verilog signal list is it has its own limitations, like it leads to long error-prone declarations and poor scalability. So how to overcome this? What we have to overcome this is what is called as interfaces in System Verilog. So interfaces are nothing but they group this entire bundle. They combine all these ports which we saw just now. They are bundled into a single wire or bus, you could call, which we name it as interface. So this improves modularity and reusability. And whenever I want this bundle in any other program, I can just call this interface. So how do I define this bundle? I define it inside interface, end interface. So I have interface followed with interface name, and then I enclose it with end interface. So in this enclosure, I define all the wires which need to be bundled. So for example, I'm bundling 8-bit, generally 8-bit bus here, which because I have parameterized width as 8, so width will be replaced with 8, 8 minus 1, that is 7 colon 0. So that data bus is bundled inside interface. So this data, which is 8-bit. Then I have a logic valid, a logic ready. So valid, ready, and then it has an input also, which is clock. So this entire thing gets bundled in what is called as interface. So whenever I want all these signals in my module, in my program, I just call this interface with the name bus underscore f. So whenever I call this bus underscore f, I'll have in my module the entire bundle containing 8-bit of data, 1 bit of valid, and 1 bit of ready. So in this way, I can achieve reusability, I can achieve modularity. So here in this example, interface bus underscore if you want to override width based on your requirement, I parameterize it. This time I've parameterized it to a value of 8. This interface has input clock, input logic clock, and the things being bundled are data, valid, and ready. Then I can call it in any of my module based on my requirement. So I have module top, logic clock equal to 0. Then I'm instantiating this interface in my module, right? So bus underscore if is being instantiated with the b underscore if underscore inst being the instance name for this interface. And I'm overriding the width value here. Instead of 8, I'm overriding it by 16. I'm generating a clock here. So always hash 5 clock equal to not clock. So this top module will generate a clock generate a clock which is of 10 time period, correct? So on and off together is 5 and 5 together, which is 10. uh, that is the clock period. So this will be passed into the bus interface, and then it has its bundled wires, which is an 8-bit data, a 1-bit valid, and a 1-bit ready. So this way you can invoke an interface. So instead of defining the port again and again in each of the module, wherever you want this specification in your module, you can just call this interface inside the module. So this is how we achieve modularity. So how do you do port connections using interfaces? We'll just take one bigger example and understand the concept, okay? So I have here a module which is by name producer. I have another module by name consumer, right? So I need an interface to the producer. I need an interface to the consumer. Okay. See, what do I do? I need some port list for each of this, right? So I have a module top which will invoke these two instances. So I have module top. So it has its clock which is initially declared to 0. Then it's also instantiating a bus interface. So this module top is instantiating a bus interface, so which is nothing but v underscore if, which is our earlier module, which has clock and which has data and valid and ready, right? So if you go back to your previous slide, so that has data, valid and ready. So that's my interface, right? So let me write that interface. The name of the interface I'm calling it as b underscore if. That's the interface. So it has a clock, it has data, which is 8-bit, it has valid, it has ready. Correct? So these are my 4 different modules. Now top is invoking all these 3 modules. So what will it do? It will first invoke the interface. So that's been invoked here. So when I say bus underscore if b underscore if, this instanced interface will be invoked. So it will have all these parameters inside it. Then I'll be invoking producer p with an instance name p. So I'm invoking p and I'm passing the bus as the parameter to it. Now the producer will have an interface, and then I'm invoking consumer with an interface again, correct? So that will also be invoked with the instance name C. So two instances are invoked, one instance of producer with the name P, one instance of consumer with the name C, and this interface with an instance B underscore if is invoked. I'm trying to establish this connection now, okay? So once this is done, also in my top module, I'm generating a clock which is toggling between 5 clock period. So my total time period will be 10 time units, right? Now, how will this work now? So this has been invoked. So producer P gets instantiated, the interface gets passed as a parameter to producer, then always at passage of B dot clock. Now this clock belongs to B, right? Because B is, this clock is passed as a, this has clock as its uh, parameter which is being passed, right? So in the interface, if you remember, I'm passing clock in my interface, this clock, which is nothing but which is toggling between every 5 time unit, right? So that is being passed. So this gets toggled. So for every passage, what happens always at passage inside the producer, b.data will create some random number, so unsigned random number. That's what is it's creating. So this producer has an interface getting connected, right? So this interface has data, valid and ready in it. Okay, so we have data, valid and ready. Right now, this belongs to this data valid ready belongs to producer as well as consumer, because I'm instantiating, I'm passing this as a parameter in both, right? So p dot data, this data, what it does, it generates a random number, and then it also does valid equal to 1. So p dot data has a random number, p dot valid has a value 1. Correct? So now inside the consumer, so we have generated some random number, assume it is some 123. Okay. So what happened? P dot data, let's see, it generated 123. Let's say P dot valid, I'm asserting a value 1 on it. So it's 1. So now the consumer always at passage of B dot clock. So again, consumer also responds whenever there is a POSIX at b.log. It sees whether b dot valid is 1. So whenever this becomes 1 only when the producer asserts 1 on it. As soon as producer asserts 1 on it, the consumer also has its own data and valid. So it will be reading valid. So whenever this is 1, which is nothing but 1 made by the producer, so what happens to consumer? It displays b dot data. That is, whatever is on the data, it displays here. So b dot data gets displayed, right? So producer is used to generate p dot data and p dot valid. It's used to generate this. And what's the function of consumer module? Consumer is to read the p dot data. And when should it read the p dot data? How have I written my program? It should read p dot data only when p dot valid is 1. You're understanding? This is how P and C instances of producer and consumer can communicate with the ports. Now, the ports being converted to interface. That means it's like a bundle. So they both can communicate on this port via interface, which becomes very easy to understand and very easy to reuse. So I am able to achieve modularity. I'm able to achieve reusability. So that is how port connection using interfaces work. Okay. So let's see one more. So let's see this example. So if you run this on EDA Playground, what I'm doing here is whatever I've explained to y'all in my earlier slide, the same thing. I have copy pasted this code on EDA Playground and I'm seeing how they work. Okay, so run the code and please see how you get the responses between producer and consumer. Okay, so you can also have interface instantiation and parameters. So you can parameterize all your instances of interfaces. So for example, here I have module top, logic clock is 0. Then I'm just instantiating interface inside the top module. So what is my instantiation? Here I'm overriding the parameter. The original parameter of the interface is address underscore W is 32, data underscore W is 64. That means address width is 32, data width is 64. But am I overriding it now? Yeah, I'm overriding it by 16 and 32 respectively. That's the advantage of hash of parameter. So whenever you call interface in any other module, you need not keep it fixed to 32 and 64, but you can, based on your requirement, you can change the width of address and data by overriding their values. So they have to be specified using parameter, then only you can override the values. Okay, so now I decided that I want the same interface. I want them. I want all the port list, but the only thing is I want for this interface the width of address and width of data to be different. That's the reason I've changed it to 16 and 32 respectively. Okay, and else all other things I've kept the same. Okay, so access underscore if hash of dot address underscore W of 16 comma dot data underscore W of 32. That's what I've kept here. Then followed with the other signatures to match, right? So this is the instance name of the interface, and this is what you're passing to your, this is the communication, right? You need to pass the clock. So always you generate a clock of 5 time unit and you call this instance in your top module, right? And so whenever you call this instance on your top, in your top module, the values are overridden here by from 32 to 32 and 64 to 16 and 32 respectively. Okay. So now what is mod ports? Now interface we discussed. Interface is nothing but whenever I want all the entire port list to be bundled together, and entire bundle is reused in each of the module, but just by calling the interface. That's the method. That's very easy to access the ports. So one more use which you can do with interfaces by making them mod ports. Now, what are mod ports? Without mod port, if you use the interface, then manually you have to declare signal directions in each module. Now the port has input, or the port can be output, or the port can be in out. So when you're putting it in a bundle of what is called as interface, and you're using it in using this bundled interface in different modules, these port list, you need to manually declare them. They may become input in one of the module and they may become output in another module. We don't know. So you have to declare them. But then instead of manually declaring the directions of each signal in the interface, what you can do is you can use mod port there. So what mod port does is it will tell the direction of each input or each port which is being used in the interface. So let's see how it's done. See here, I have a mod port. Uh, I have an interface by name bus underscore if. So bus underscore if is the interface. And what are the things bundled in the interface? So this is interface. There is a data, which is an 8-bit data bundled and valid and ready. Correct? So these are bundled. So we have end interface here. But then in between this interface and end interface with the bundles, I have what is called as mod port master. I'm creating two divisions, this bundle is broken into two bundles now for my requirement. So the entire bundle is broken into one as master and one more as mod port slave. And what I'm doing here is this data valid and ready in the master has some direction. So data is output, valid is output, and ready is input for the master, while data and valid become input and ready becomes output for the slave. So it's like I have a master, I have a slave device. Okay, the interface is connected like this, but then here it goes as an output, but here it becomes an input. So slave will take it as an input. Here, from here it goes as an output. But at slave, when you see it from the slave's perspective, the signal is the input to it, right? Again, when it comes to valid also, master sends some data on the valid, so that becomes the output on master, while slave takes this as an input because it reads that on the valid signal, right? And then we have ready. Ready is nothing but slave tells when it is ready to take the data. So that becomes an output for slave, and the master will be waiting for the slave to send the signal on the ready signal. So that becomes input, right? So we have master and slave with data valid and ready having meaning which is different for master and slave respectively. Okay, so we need to mention the directions there, and that is how we have done it. Then end interface. So producer, the rule, for example, if I want to use them in the producer and consumer module, then how can it be used? Let's see that. Okay, so for producer, the role of producer is master, probably. Let's assume producer works as a master, and a consumer works as a slave. Imagine we have that. Okay, so this is producer, this is consumer. Now how do they interconnect with each other using interface and mod port? Let's see that. So for example, I have written this code which you can run on ADA Playground. So I have interface. The name of the interface is bus underscore if. So interface bus underscore if. The parameter clock being passed as input variable, and what have I bundled inside the interface? 8-bit data and valid and ready are the signals, which these are all bundled in the interface. And now this interface is broken into two divisions. One is using mod port. So two mod ports I have created. One mod port is, so the interface is like this, right? So it's an interface. So in that I've created two divisions. So this is mod port master and this is mod port slave. Correct? So the interface data valid and ready, master has, and slave also has the same thing, data valid and ready. But in the master, data and valid are output, ready is input. In the slave, data and valid is input, ready is output. See, when I want to give different directions for the same port, based on where am I calling that interface, in which device I'm calling the interface, uh, then I have to use mod port. If but the directions are same in all the modules wherever I'm calling the interface, then mod port is not required. But in this case, I'm calling interface in two different modules. Wherein one of the module behaves like a master and the other module behaves like a slave. So now, when I have a master slave module interacting with each other on an interface, then the directions of these signals matter, because the directions of these signals on master will be different, while the direction of these signals on slave will be different. So in such situation, you have to use mod port there, right? So that's the reason we have done this. We have bifurcated the signals as master and slave. And now when I want interface on my producer, I'll be using the master mod port. Whenever I'm using the interface signal on a consumer, I'll be using the slave mod port. That's all. It's as simple as that. So I'll be using the slave mod port. Okay. So where is this mod port situated in? It's situated in bus underscore IF interface. So I have to declare it as bus underscore IF dot master B. So master B is the mod port belonging to bus interface bus underscore F. Similarly, slave b, right? Bus underscore if dot slave b. This is how you will be calling the mod put slave here. Okay, b is the name given to the slave, b is the name given to the master, uh, but it's bus underscore if dot master. And so this b is bus underscore if dot slave, right? So this is how you declare. So that's the difference. Now I'll be generating some 10 random numbers, so repeat of 10, and for every clock edge or pause clock edge, b dot clock, right? So this entire interface has an input clock which toggles for every 5 um, time unit, right? So total time period is 10. So every 5 it toggles 5 and 5, which is passed as a clock input to the interface. So whenever there is a passage of this clock, whenever it's a passage, the function of the producer is to send some random value and also to assert one on the valid signal, right? So that is what it's doing. And at passage of b dot clock, if of b dot ready begin, dollar display producer b dot data. So what it's doing is it's generating a random number, it's asserting one on the valid, and then for the next passage, first passage, it's storing the data on the b dot data signal. It's storing some random value and it's asserting b dot valid as 1. And for the next passage, what it does for the next passage, it will see whether ready is high. That means whether slave is ready to accept the signal. It will be reading that. So that will be the input on the producer. Okay. So when slave has sent a ready signal, producer says it has sent the data, and then it asserts 0 on valid. Okay. Till b dot ready is high, it will put the data on the channel and wait for the slave to read the signal. Okay. So coming here, so whenever at every passage, it will make ready equal to 1. It will always make ready equal to 1 for every passage. And then it will see whether valid is 1. Okay. If valid is 1 and ready is 1, what it does, it receives the signal. So it displays it, which is on b dot data, right? And ready will be 1 now, indicating to the producer that the consumer has read the data. So it will say producer has sent the data, and in turn consumer has read the data. Then it asserts a valid equal to 0 here. So there is a communication between producer and consumer on the interface cable. or you could say. And this cable or interface bundle is divided into mod ports, one mod port belonging to the producer, since producer is working as a master, and one mod port belonging to consumer, since consumer is behaving as a slave. Okay, and they communicate with each other using the ready and the valid signal. Okay, so data is sent by the producer, data is read by the consumer. Okay, so this is how they work. Okay, so in the top, so I have to instantiate these modules, right? So I'll be instantiating them in one more module, which you can also call as test bench. So inside the top module, I'll be instantiating the bus interface first. Then I'll be instantiating the producer and the consumer, and I'll also be generating the clock signals here, which is with 5 time units, and then this instantiations will be communicating with each other, and this happens till 200 time units. At 200 time units, there is dollar finish, which ends the execution. Okay, this is how my program works for interface with mod port. Next topic is interface references. So you can also pass an interface by reference to task or function, and allow modification to affect the original instance. For example, I have my top module here, or you could call this as a test bench, wherein I've instantiated my interface with the instance b underscore if. And then inside the block of initial, I have called a task, which is init underscore if. This is the task, and I'm passing my interface as the parameter of the task. So, and I want to make permanent change on the port list, which are bundled in the interface. So I'm passing it as a ref. So that is with the address, right? Reference stands for it accesses the address of the ports which are bundled in the interface. So when I say ref, permanent changes happen. Now, when I say b dot data is 8 tickets AA, b dot valid is 1, b dot ready is 0, these are changed permanently. And so when the task returns back also, these changes reflect in the original instance. They do not get this is not a temporary change. Okay, that's a permanent change that happens on the port list because I've used the syntax ref there. Okay, so this is about the introduction about interface and how interface can be converted to mod port, and then how I can use interface in a task, and permanent changes can be made on the ports inside the interface using ref. So the continuation of that, let's see in the next module. Thank you.